Hi, and welcome to Live from the Lab. During this series, we're going to explore different Bruker technologies, how they work, what they're used for, and give you some tips and tricks with how you can get the most out of those techniques. Today's topic is, what is XRM? And I'm joined by our resident expert, Dave Sampson.
Morning, John.
So, Dave, to start out the day, I guess, what is XRM?
Well, really a short answer is, we're all familiar with CAT scans. You go to the hospital, you get hurt, you get a CAT scan. Well, it's that same technology, just geared more towards the research, materials research and science.
And when you say geared towards, how does it differ than that instrument that we might see at a hospital?
Well, your medical CAT scan will typically have a resolution on the order of 250 to 500 nanometers, or 250 microns. That's a little bit too big for what we want to do. So the XRM will typically have resolutions down to, say, a few hundred nanometers.
And what makes this different than say, just a CT? Why are we calling it a microscope all of a sudden?
Well, it's a microscope because, we're getting high resolution. So CT, CAT, computed tomography, is the technique. It's the mathematics. It's the science behind the technique. But the instrument, how you use it, is a microscope.
Okay, I'm familiar with light microscopes, say SEMs, things like that. They're basically giving us a blown-up view of the nano world around us.
Exactly.
Okay. And is there anything else that differentiates then this technique, X-ray microscopy, from traditional light microscopy?
Well, in light microscopy, you have a series of optics and lenses.
Yeah.
And magnification is through adjusting those lenses. In XRM, it's called geometric magnification, where you're moving the sample back and forth to basically create a shadow that relates to the resolution and the magnification.
And then just like the medical CT, you also get a three-dimensional view.
Correct. You get three-dimensional data that then you're allowed to analyze, cut, slice any way you want.
So to explain this a little bit more in depth, we have a video that we've put together about what is XRM and how does it work.
Microscopy is a quintessential technique used to understand the microcosm around us. Since the 17th century, microscopes have used visible light to provide a magnified view of miniature objects, enabling scientists to make breakthrough discoveries. A view into the nanoworld became possible in the 1930s, when a team of scientists led by Ernst Ruska invented a microscope using electrons instead of visible light. Both visible light and electron microscopy provide detailed images of a sample surface. Qualitative and quantitative analysis of surface properties can be performed. These results allow components and materials they are made of to be pushed to new limits. But what if analysis could be extended beyond the surface? What if investigations could be performed deep into the sample, revealing the three-dimensional structure? What potential could be unlocked to push material properties even further, or to induce new properties? X-ray microscopy is an emerging method which allows researchers to do just that. Based on a technology called microcomputed tomography, XRM combines three-dimensional imaging with advanced visualization and 3D evaluation tools. X-ray radiation is a very high-energy light capable of penetrating objects that are opaque to the visible spectrum. Cone beam X-ray imaging results in a two-dimensional radiograph, showing the transmission of X-rays through an object. Low-density volumes of the object allow high transmission, while high-density volumes allow low transmission. With a point X-ray source, magnification and illuminated volume can be adjusted. Larger coverage is achieved by moving the object closer to the detector, while higher magnification is achieved by moving the object closer to the source. The source to detector distance also plays a pivotal role in balancing magnification and coverage. Moving the detector closer to the object results in higher coverage, while moving the detector further away yields higher resolution. Unfortunately, if multiple features are present inside the object, the image is hard to decipher. This is overcome with a technique known as computed tomography. Several projection images are collected as the object is rotated. The object is digitally reconstructed, revealing the position of features in the object. As with cone beam microscopy, contrast in the three-dimensional model comes from the absorption difference of the features in the object. Microcomputed tomography extends the resolution of CT into the submicron scale by using X-ray sources with finer focuses, object stages with higher precision, and detectors with smaller pixels. X-ray microscopes combine micro-CT hardware with specialized software for quantitative analysis of three-dimensional models. This includes object counting, size determination, size distribution, and orientation analysis. The 3D model can even be exported to a 3D printer. X-ray microscopy is used across a wide variety of applications, from maximizing well efficiency by determining the open and closed porosity of core samples in the petroleum industry, to measuring the homogeneity of pharmaceutical coating thicknesses to dial in API uptake rates. Using XRM, engineers can identify defects within the internal structure of complex components created with additive manufacturing, or maximize the performance of composite materials by verifying the orientation of fibers buried in the resin. Innovations in instrument design, ease of use, and computing power have increased the availability of X-ray microscopy. Measurements once only available at large research centers are now commonplace in benchtop microscopes, allowing scientists to uncover new insights into the world around us.
So I think we're all on the same page now about how XRM actually works, but let's go a little bit more into depth on those applications. So what I saw there was that this is often used in pharmaceutical industry. Dave, how is it actually used in that pharmaceutical industry?
Well, there's a lot of things you can do in the pharmaceutical industry. You can look at packaging. Since it's an X-ray, you're actually able to see the pills, the medicine inside the containers.
Okay, so some of these modern drugs that are formulation.
So like you can actually do QC, QA, like put way down the production line. But also you can get into the pill and look at what is my active ingredient distribution? What are the thicknesses on my coatings? Are they uniform? You know, things like that, things that an engineering manufacturing line would like to look at.
And you'd be sensitive to the difference in density of the different materials. So there's even the chance to do some quantification or determine how well mixed it is.
Correct. This X-ray, XRM is sensitive to the attenuation of the X-rays to the material. So each material is going to have a slightly different attenuation. So we can actually look at a material and figure out how much of each part there is in that sample.
So what about in that geology sector? How would an instrument like this be used for geology?
A key use for geology is not looking at the materials, it's looking at what's not there. So pore. How porous is the material? Are the pores connected? Are they not connected? Do you have a lot of little pores? Do you have a lot of little big pores? And that actually, tells you a lot about, like, say, the hydrology of this material.
And that's important for somebody like the petroleum industry.
Absolutely critical to them.
Okay, and that's an interesting point, is that we can both look at the presence of matter, but also the absence.
Correct, absolutely. And when you're talking about the absence of matter, defect review, looking at, say, 3D printed parts, we can actually look inside the part to say, do I have voids? Do I have areas that are dense? Something that you can't actually get at by looking at a 3D part.
So, and when it comes to then, say, parts and components, I mean, you can only look at small things, right? You couldn't look at something like, say, a phone.
Absolutely. No, we have phone.
No, you can.
Yeah,
okay.
yeah, no, it's big enough to look at a phone. And if, say, the part is actually too big, we can actually scan around and do things like spiral scans, where we move the sample up and down and we scan sections at a time and stitch it all together.
Okay, and even, say, this phone, for example, which has some kind of a glass, a plastic, maybe aluminum or something like that.
Yeah, absolutely. We can see all the different components and break them out. And you can tune your X-ray to say, do I want to look at the metal components more than the other components?
Okay, and now these instruments, we're going to go and see them in a minute in the lab itself. But are they simple to operate? Do you need a PhD?
Very simple.
Okay.
Very simple to operate. It's one of those instruments that a basic user can use and an extremely advanced user can use. They can be set up to run simply, but you have so many things that you can configure to get the most out of your experiment.
Now, would you say that it's closer to using a light microscope that we're all pretty used to, or is it more like running a TEM where there's a lot of sample prep?
No, it's a light microscope. I mean, it's a sample in, push the button, set a few parameters, and you're ready to go. You can run it. You can get a sample ready to run in seconds.
So I think on that note, it's time to head over to the lab and just see how easy one of these instruments is to operate. So Dave, now that we're in the lab here, I see that you have a few different instruments. We have this very, very large instrument. So what would this be used for?
So this is our SkyScan 2014. This is the ultimate in our production, in our product line. This will give you nano scale resolution. So you have 100, say 10 to hundreds of nanometers of resolution.
So you actually get into that nanometer scale with these things?
Absolutely,
Okay.
absolutely.
So that's really on the order of those traditional light microscope type solutions, but this is also giving you the internal.
Correct. Yeah.
Okay. And then over here we have, it looks like a benchtop. Now I'm guessing that you must have a lot of extra equipment somewhere else, maybe in another room?
This is the whole instrument. This is the SkyScan 1275.
Okay. So looks like we've got the instrument and maybe a pretty beefy
computer. Absolutely. That is one thing about X-ray tomography, X-ray microscopy, is one of the things that's brought it to the consumer in the last 10 years is the advent of high-end graphical processors that you and me can actually use.
Okay, so this has a pretty high-end GPU.
Actually, 20 years ago, you needed, a large computer, tens of thousands of dollars just in the computer.
Yeah, it might be as big as this room.
Exactly.
Okay.
Now
right there.
That's an amazing device.
Yeah.
And, this thing just plugs in and goes.
Okay, so do we need any special power? To use high power?
No power, no cooling lines, nothing.
Okay.
It's just good.
So yeah, I mean, how do we do it?
Well, like I said, this can be programmed to many levels.
Yeah.
You're experimental, but if you want to do just some basic research, I can just set it up, push the button, got my sample.
Okay. Looks like a blue M&M or something like this.
Sure.
Maybe a chocolate candy.
Yeah.
Okay.
And it's up and running. And so the red light tells us that our X-rays are on, but this is a completely safe. You don't need any special X-ray monitoring for this system.
So even though the light's on, we don't have to be concerned about any sort
None
of exposure?
whatsoever. I mean, each state has its own requirements.
Okay.
But no, we passed every regulation.
All right. So these are kind of built on that Bruker history of the strong safety.
Absolutely.
When it comes to the instruments. But just push the button. It looks
running.
like it's
you
on.
can see the sample slowly rotating.
Okay, and then down there in the corner, looks like we have a live view of the sample on the inside.
That is correct.
Okay. And so that sample now, you're saying that it's rotating.
It
on
is.
A small
It's
stage.
rotating. We're generating hundreds of images, hundreds of X-rays, radiograms. Now, then we will reconstruct into our three-dimensional data.
And all that data is being saved to the computer. That's got to be a pretty big file.
Yeah, that is one thing that you are dealing with, tens of gigabits, but we have the computer processing power to deal with that.
Okay, and if you had a material that was maybe a little bit lighter in terms of its weight, maybe it's a very thin plastic.
Yeah.
Would you make any adjustments to the instrument?
Yeah. So the lighter the material, the softer, the lower the energy X-rays.
Okay.
So this is kind of a medium material. But yeah, so our system has the capability of going from 25 kilovolts all the way up to 100 kilovolts.
Okay, and then the larger machines, I'd imagine you can.
This one, the big SkyScan 2214 can go up to 160 kilovolts. It's got a little bit beefier X-ray source than this guy had.
So a little bit more punching power.
Exactly.
So it looks like the light turned off.
Light turned off.
Okay, the door's opening.
Door is opening. There's my sample.
So that's pretty simple. It looks like if I was to remove this, we don't have to worry about the sample falling in or
absolutely
anything like that.
It's going through an automatic reconstruction.
So
it's
that would
taking
be
those hundreds of data, those hundreds of radiograms, and it's converting them into a three-dimensional image for us.
So I imagine something like this is going to take us 30 minutes, an hour.
No, this will just take a minute or two.
So all of that comes from the computer itself. Now, does it use the processor? Does it use a GPU?
It uses a GPU.
Okay.
And unlike a lot of companies, we provide all the software you need.
Okay,
so you
really?
have your acquisition software, you have your reconstruction software, and several different packages to analyze and view your data.
And is that on some sort of licensing basis, like Office or something like that, where, okay, you get it for a year and then?
No, you get basically unlimited licenses.
Okay. So you get a bunch of licenses and it lasts.
Right. And so everyone in your research group can put this, can use this on their system.
And you get the software for doing the measuring. You get the software for doing the reconstructions.
Right. And then there are 2 graphical packages and 1 really high-end analytical package for for measuring how many, how much, what are
Yeah.
the differences, all the various things that you would be interested in measuring in your sample.
Now, in terms of the samples themselves,
Yes.
from the video, I remember the closer you can get the sample to the source, then the better the resolution will become.
That is correct.
Okay, and then the farther back we go, the more the coverage.
Correct.
So the limitation just kind of centers around your resolution and coverage requirement.
Correct.
Okay, and this instrument, it looks like we also have some sort of a little filter or something.
Yeah. So on this system, it's a basic system, we do have the option of having an aluminum filter or a copper filter.
And why would you use that?
There's a couple of reasons, but typically it's if you're looking at a more dense material, you want to refine the energies down to the higher energies to get rid of. There's some effects with the bremstalling. Basically, you get a couple of material artifacts. It's easy to remove.
Okay, so by limiting that radiation, you get a
Correct.
little bit cleaner picture.
You get a little
in the end.
picture, yeah.
So it looks like the reconstruction here is complete.
Reconstructions are done. We're headed off to the graphical analysis package.
All right, and there we go. It says 100%.
And there we go.
Okay, and it looks like you might have some controls here. Maybe we blow it up to. So it even knows it's blue?
No. I cheated. I made it blue.
Okay, so you can change the color.
You can change the color. You can cut inside. So you have candy coatings with the peanut on the inside. This is chocolate. Again, this is all artificial coloring.
Now, after this is done, would this be irradiated? Is it not safe anymore?
Oh, it's perfectly safe. You can take it out and eat it if you really wanted to.
So we don't have any problems
There's no problem.
Okay, and the sample is basically, it's not hurt, not destroyed.
No,
not
it's
affected.
completely a non-destructive technique.
Okay, great. So we could go on and use this product. So yeah, I mean, I can definitely see here on the edge there, it looks like a shell.
Yep.
And then we have a little area here with some little pores in it, maybe. And then that looks to be what, the peanut?
That is the peanut.
With a little crack
in the middle.
going right in the middle. So there we can see both the presence and the absence, and what's that contrast coming from?
The contrast is coming from chemical differences. So, like I said, X-ray microscopy is sensitive to the atomic number of the material and the density. So, granted, a lot of this is carbon-based, but we're seeing this is a more dense material than this.
Yep.
Right, and then this is even a lighter material.
And so, does the analysis stop here at these qualitative things, or can you?
Absolutely not. Absolutely not. We could, if I wanted to do quality control on these, I wanted to look at the sample size. I could set up a program. I could run 500 of these, and I can do data analytics on the size, on the shape. What's the thickness? This goes back to the pharma question: is if you're in pharma, you want to know exactly what the coating thickness is here.
Okay.
I can do statistical analysis. I can tell you exactly what the thickness of this coating is, what the average thickness of the coating, with the thin, with the thickness, all that, which is like key information to feed back into the system.
Okay, so you can get the thickness of different things, the size, the number of the pores, things like that.
Correct.
From this technique. Well, this looks like a really intriguing technique. I know, being a material scientist in the past, I was never aware that you could use X-rays like this. I knew that they had techniques in the light microscopy realm to do 3D.
Right.
But the sample doesn't really have to be clear or
There's
somewhat
lots of caveats
visible
to that. Exactly.
Yeah. But here we can actually start looking at samples that are opaque to our normal spectrum. All right. So with that, I think we're going to head back to the studio and answer some of the questions that have come through on the live stream. So, Dave, it looks like we've had some questions come in through the live stream.
Okay.
The first one is, can this be used instead of SEM for a deeper visualization?
Absolutely. SEM may get higher resolution, but you don't get that three-dimensionality that you can get with an XRM.
Yeah, so I think that you're saying it just there. You've got a little bit more resolution maybe with SEM.
Right.
Yeah.
And there are techniques in SEM, but they're destructive,
Yes.
right?
Yep, to go deeper in.
To go deeper in, right?
Because really the penetration depth of that technique is visualizing just a surface.
Right. There are these complicated techniques where you do fib milling, and to generate a 3D image, but that is a destructive technique and takes hours, if not.
Yeah. And the next one is coming from Jay, and it says, how can you obtain material properties for large curvature parts?
Large curvature material, so that's gonna need more information, but we can, we can take that information, and it depends on what you want to get. You can compare the data that you get off of these for manufactured parts, and then compare them back to the original SolidWorks files.
Oh, okay, so you can actually take this this rendering out.
Yes, exactly.
As like a STL.
As like an STL file, and then you can feed that back into your SolidWorks files, and then there's techniques to compare and contrast differences. Did I actually make what I thought I made?
So you would actually see then visually what the difference is between the two. All right, the next question would be, there's a lot of different terms for resolution out there. And so Fabian is asking, what is voxel resolution?
There is a lot of that is a good question. So you have the voxel resolution, which is how small can I make a 3D pixel, a voxel, right? So that is one measurement, and that's a function of your detector. And there's also resolution based on what's the spot size of my X-ray. So typically, like for the 1275, and for other instruments like that, the X-ray spot size is about 5 microns. Now I can set up a detector on some of our systems, especially on our 1272, where we can put many voxels onto that 5 microns.
Yeah.
So
So it sounds like voxel resolution comes from the detector itself.
Correct.
So if you have a very, very good detector with tiny pixels, you can get a very, very small voxel resolution.
Correct.
For example, I think on the 2214, that number's around 60 nanometers.
Correct.
But then when you take into account everything, you take into account the sample rotating, you take into account the source size, which is a big thing.
Right.
Then we're talking more around the 500 nanometer mark in terms of what that ultimate resolution is.
Yes.
And no matter what you do in terms of making the detector pixel smaller, it's not going to give you true resolution in terms of separation between two objects.
Exactly.
Okay. So the next question that we have is coming from Kimberly, and it says, can you analyze liquids?
Yes, absolutely. Granted, with liquids, you have motion, so that gives you some problems there. But if you want to say have something in a liquid, absolutely. You can put your sample in a liquid, in a container, and image it. It's done all the time.
And so if you were to, say, continually add to that solution, you could actually see, say, a reaction occurring.
Exactly. And there's been studies done with like salt growth on material or rocks, or dissolution over time. Correct.
And it looked like there was a lot of room in there, a lot of feed through and stuff like that.
Absolutely, right. And there's a lot of custom cells out there to help with these experiments.
So then the next question is from Abdul and Harshita. And the question there is, how does this compare to both SEM and TEM? So we talked a little bit about the resolution. We talked about penetration depth.
And again, SEM and TEM are both 2D type imaging, where you're seeing, you are getting penetration into the sample, but really an SEM generates a 2D representation of your sample.
Yes.
In XRM, you get a full 3D image all the way through. You can see in and out, you can see all the way through your material.
Yeah, and in terms of resolution even, at beamline, so if you're going to go to a beamline user facility, you can actually obtain resolution that is very, very, very small.
Absolutely. And interesting, that was how, XRM was done up until, say, 15, 20 years ago, is you had to go to a beamline to get this type of measurement.
One other thing, actually, I'd like to point out about the electron techniques is sample charging.
Yes.
So do we have any issues with sample charging here?
No problems whatsoever.
Okay. No. And so sample charging means when you have an insulating sample, it's going to accumulate electrons.
It's going to cause some charging effects, and it gives you a lower quality image.
So then yeah, you won't be able to image the sample unless you coat it with something like a carbon, something like that. The next question, can you get HR images? So I'm guessing high resolution.
And it depends on what's high resolution.
Yep, resolution is always a question that comes
right.
up.
Yeah, and like you mentioned, we can go down into the, hundreds of nanometers.
Yeah.
And all the way up to, hundreds of microns.
Yeah.
So really, that's the functioning range of an XRM.
And generally what I've seen is that people tend to really push the limits in terms of the smaller size.
Correct.
And most people who get one of these instruments, they actually back it off a bit, and they're using more in that micron scale.
Yeah, yeah.
So in terms of data size, that's another thing to come in, right? Is that the smaller the resolution, well, the more data points you have.
Sort of, yeah. Detector size, but yeah, you're sitting there scanning. If you want to take a really high resolution image, you're quite often going to take even 10,000 or say 5,000 scans, which is going to be a large data set.
Yeah, and the other way I like to think about it is that there's a certain measurement component or statistics component to that too, right? The smaller the bins become.
Correct. And when you're getting higher resolution, like I said, smaller bins, you got to think about what is my photon flux onto my detectors.
Yeah.
Then the measurement times will take a little bit longer too.
Okay, and that's just due to an effect. If we thought about shooting, say, a fire hose at a sample, and we had a bunch of 5-gallon buckets, each bucket ends up with more water in it.
Correct.
Whereas if we used a bunch of small cups, well, each one has less water in it, so you're going to have more statistical variance.
Right.
Okay, from cup to cup in that example. So the next question is there a minimal sample size? So we kind of talked about maximum being what?
No,
fits.
not really. No, the minimal sample size is really the smallest sample that you can mount.
Yeah.
Yeah.
And the smaller
the smaller your sample, the higher the resolution. Because remember, with the geometric magnification, the closer you can get that sample, the center of your sample to the X-ray source, the higher the magnification you're going to get, higher the resolution. So yeah, the smaller samples is actually the way to go.
And then on the larger side, we can measure something about as big as 300 millimeters or so, right?
Yeah.
Okay. So you can get a pretty large one. In terms of length, I know that there's also a fancy feature called helical scanning.
That is correct. That is correct. And then helical scan, basically, instead of rotating your sample in one fixed height, it actually runs your sample through a corkscrew.
Okay.
And what that does is it allows you image all the way through that field. So you can do something like your phone, right? Where you can image
this and...
Right. And it also helps in imaging. There's other techniques with this helical scan, which helps to make your images sharper, especially if you're trying to look at something flat like this.
Okay.
The helical scans actually give you much better data.
All right. And the next question comes from Raja. Actually, it's maximum sample size. So I think that we just talked about that one. So now Vicenta is asking, could you analyze rock samples with embedded liquid hydrocarbons?
Oh, absolutely. Straightforward. Yeah, there's no problems with that whatsoever. The void, not being an air void this time, the voids are filled with liquids. So
yeah, in fact, I think in geology, one of the more challenging would be going to a very, very dense mineral, like if you had something with lead in it and things like that.
Correct. Then when you're going from a very dense material and trying to measure a lighter material inside, that becomes a little bit harder to experiment.
Yeah, I know when we were trying out these instruments, there was actually I brought in some Gold Rush pay dirt.
That is correct.
Yeah, and so we tried measuring that, and you could actually see the little gold flakes, but then you start to get a little bit of a artifact near that. So it looks like we're coming to the end of our time. So thank you, Dave, for joining us today and talking about XRM.
Yeah.
So in the future, we're going to have all of our live streams the first Thursday of the month. So please join us for our next one. And thanks for joining us today.